You type a prompt into an AI chatbot, hit enter, and an answer appears instantly. Every time you do this, a physical machine somewhere consumes real electricity to generate that response. The immediate question is, how much electricity? The public conversation around this usually swings between two extremes. Some people treat artificial intelligence as a completely weightless piece of software that runs on air, while others describe it as an electrical doomsday device draining the global power grid. Attempting to find one universal number to represent all AI energy use is like trying to weigh fog with a bathroom scale. It sounds concrete, but it completely ignores the mechanics of how the technology operates. The actual electricity consumption is dictated by three highly specific variables: the exact type of task the software is asked to perform, the volume of users making those requests, and the efficiency of the physical computer chips running the math. Demanding a single, catchy headline number ignores reality. The energy cost of artificial intelligence is a highly variable systems problem, demanding context before any estimate can be taken seriously. At the most basic level, asking an AI to auto-complete a sentence requires a tiny amount of energy, often just a fraction of a watt-hour. On a per-use basis, a simple text output is a very modest computational lift. However, asking that same system to generate a high-resolution image, write a 1,000-line block of code, or render a multi-second video requires the model to hold vastly more data in its memory and execute millions of additional calculations. This diagram shows the scale of that difference. The energy required to process a short text prompt is a single tiny cube compared to the massive matrix of calculations required for a heavy multimodal task like video generation. What feels completely frictionless and immediate to a user on a smartphone often triggers a highly intensive, power-hungry workflow on the back-end servers. The energy footprint of AI begins long before a user types their first prompt. Developers must first build the model through a process called training, which is when a software architecture learns underlying patterns by chewing through enormous datasets. This training phase is a massive upfront energy event. It requires thousands of specialized computer chips running at maximum capacity, sometimes for months at a time, to process all that raw information. Once the model is trained, it moves into a phase called inference. Inference is simply the day-to-day operation of the model answering actual individual requests from users. Here is an AI model's energy lifespan. The massive electricity spike represents training, followed by the steady hum of inference. As daily requests accumulate, total inference power eventually overtakes the initial training cost. The one-time training earthquake is surpassed by the inference tide. That daily tide gets even stronger when we examine full-scale enterprise deployments. A single person writing a few emails a week creates a tiny footprint point, compared to a corporation integrating AI into its core infrastructure. When businesses deploy automated document processors, always-on background agents, and coding copilots for thousands of employees, those small individual inference costs multiply into massive aggregate utility bills. To handle that kind of corporate volume, we have to look past the software models and step inside the physical data centers where the servers actually live. The servers doing the mathematical heavy lifting are surrounded by a massive ecosystem of supporting equipment. Industrial fans spin constantly to prevent the hardware from melting. Networking gear routes data across the globe, and backup storage systems sit idle, consuming power just in case of an outage. This stacked bar chart breaks down the actual electricity use of a facility. Compute and hardware take up a significant portion, but cooling systems and idle redundancy require a huge amount of auxiliary power to keep the building functional. Estimating AI power usage by only looking at the rating of a single computer chip drastically undercounts the physical reality of the infrastructure required to keep that chip alive. The heavy power demands of these systems are a prompt to engineer better solutions. AI energy use is a highly optimizable design choice, and reducing the footprint is entirely possible. The most effective strategy is right-sizing the model to match the task. Instead of using a massive, power-hungry neural network to do a simple job like sorting emails, developers can route basic classification tasks to small, specialized models that require a fraction of the electricity. Engineers can also design the software to be strictly concise. By shortening user prompts before they reach the server and restricting the length of the AI's output, they directly reduce the amount of computation required for every single session. This flowchart illustrates caching. It's a method where a system stores the answer to a frequently asked question to avoid calculating it again. When a new user asks that exact same question, the system bypasses the heavy computation entirely, handing them the pre-saved result. Grouping multiple requests together into a single compute job, a process known as batching, improves how efficiently the chips run. Combine that with smarter hardware scheduling and upgraded facility cooling, and the power savings at scale become enormous. The massive electricity required to run artificial intelligence systems will always require careful management through highly intelligent system design. The most important question to ask is never simply how much energy does AI use, but rather how efficiently are we running this specific task.